Working in a fast-paced environment can be very challenging. Customers are demanding new features in a timely manner. The support team is waiting on those bug fixes. And on top of it all, there is always tech debt to address and legacy code to maintain and refactor. Keeping it all running smoothly can feel like a game of Jenga, where if the first few moves left the tower with a wobbly foundation, adding or removing any new blocks on top could completely collapse the tower at any moment. In engineering, it is important to have a strong foundation, so you can move fast and continuously deliver value to customers. We want to be able to write new features without breaking any existing functionality. But this can be a challenge, especially if that requires rethinking your existing data models. And things could get even more interesting if that feature or a fix is in that legacy piece of code that we all avoid touching too much, because it has hidden dangers and unknowns. And this is where having really good tests can help you out, so you can feel confident with every push to production. But what do you do if over time those tests became outdated, have some gaps, or simply don't cover enough of your core business flows for you to continuously rely on them? This is where we've turned to TypeScript as one of the tools to help us. But making big changes across an organization with many engineering teams can be really difficult. At the time, we were 6 separate teams with over 300 repos to migrate. So this was going to be an absolutely huge challenge for us. I would like to share with you how we brought TypeScript to Snyk, how far did we get, and what are some of the lessons that we've learned along the way. But before we move on, let's make sure that we're all on the same page about what is TypeScript. TypeScript is a superset of JavaScript, so all JavaScript is valid TypeScript. It adds optional static typing to the language. Type errors occur early during compilation or immediately in your IDE without having to ever run the code first. Let me show a little example. So here we have a simple function that is reading a file from disk given a file path. If the file is not found, we will throw. Otherwise, we will return a file object with properties name and text. This is what it would look like with basic types added in. We assert that the path to file is always a string, and the contents we get back is also a string. We could take this even further, and we can type the output of the function by using a TypeScript interface. So we can say that the file object always has a property name and text, and they're both a string. TypeScript has a variety of types that are useful to model some common situations. So let's take a look at just some of them. I will keep going with the file reading example. We now want to initiate the file reading by providing a file path, which is a string, but also record who initiated the action. If the action was initiated by a user clicking something, then we want to record initiated as a user. For everything else, assume this was an automated action and record the organization instead. So to model this, we can use a union type to define an action creator that can be either a user or an organization. Union types are useful where you may be returning multiple types from a function, or an input may be 2 different types. So you can see here that if we try and access the initiated by .groupID, which is a shared property, then that succeeds. However, when we try and access the org ID, for example, that is only on the organization, we're going to get an error that says that property org ID does not exist on type user. And that's because when using a union type, only shared parameters can be accessed. For others, you will have to tell TypeScript which type to assume. And here we're doing that, for example, with the as keyword. Intersection type lets us combine multiple types into one. If we had a function that validates all possible options that may be passed in before initiating the file reading, we could separate the options depending on the action and then combine the types. So we could expect here either encoding if we're creating a file, or trim spaces if we're reading the file to be passed in as an option to be validated. This is particularly useful if you are refactoring some code that might be doing multiple things at once and eventually you would like to separate it. So you can at least keep the types separate, and that helps with the understanding of the code as well. One of my favorite features is that you can reuse an interface in another interface, which makes it easy to maintain complex types by breaking them down. So let's say now we want to be able to create a new file if it doesn't exist given a file path, then get the file content if it does exist. And we also want to know if the file was just created or not. So we could type the response of this function by creating an interface with properties created, which is a boolean, and file, which we've previously had, so we can just reuse the existing interface. TypeScript also allows users to define enums, which are basically named constants, and these can be used as types. So going back to our familiar read file from disk function, let's convert the encoding to a variable, and we also want to restrict what values we support here. So we can use enums to help us define allowed encoding values, which in our case are base64 and UTF-8 only, for example. Now that we have added a new required parameter to this function, you will get a compilation error straight away. So this happens because we should now be passing the encoding as well, and the values we pass can only be the enum values that we've defined just now. So this is a nice way to control allowed values all in one place. So what would happen if we try passing UTF-16, for example, into this function? Well, actually, before you even run any code, you're going to get an error. Again, either in your IDE or during compilation, and it's going to say that argument of type UTF-16 is not assignable to parameter of type file encoding. It will go even further, and if this is the only code in your file, it will tell you that you are not using this function at all, so you can just go ahead and delete it. TypeScript can also infer the types from context or when variables are initiated, so there is no need for extra verbose typing. It also comes with many IDE integrations for signature hints, refactoring, find uses, and so much more, making exploring a large complex code base and refactoring much easier. In all of these examples, I am using VS Code. You can see here we're using a third-party library called Semver, and because it has typings included, we can see the available functions and parameters that we could use and pass in. After chatting about moving to TypeScript during our engineering weekly meetings, we decided that it would be best to kind of jump straight in and choose the code base that would benefit the most from type checking. And that happened to be our biggest and oldest code base. And this isn't something that you would normally do when trying out something new. But with so much legacy code that we constantly had to rewrite and refactor, this was really going to give us the biggest return on our investment. So we figured out the initial effort would only be about one day to just do a very basic conversion from JavaScript to TypeScript and allow us to have this hybrid application that we could deploy and then gradually convert more and more to TypeScript. So we added a very simple tsconfig.json, and the key property was to enable allow.js to be true. And this meant that we could keep the JavaScript and the TypeScript files together in the same repo. We converted just the main index.js to index.ts so that we could test the entire setup. And this is what it might look like. It's mostly updating imports so that we upgraded everything to ES6 as we go along. And immediately we saw some things that just would not work for us. Our entire code structure had to change because we needed to build everything into a dist directory, and it just wasn't structured like that. So we had to introduce a top-level source directory and move everything in there, which was really simple to do, but it did generate a huge Git diff in our history. And now we were ready to try again. And as soon as we run our test, boom, we've realized that our testing tool Tap doesn't actually support TypeScript. And this was almost 2 years ago. So unfortunately, that meant that we needed to create our own fork of Tap and create a script that could run our tests with TSNode instead. And overall, this wasn't hard to do, but it did add about an extra day to our original estimate. By the time we were ready and the tests were running, it was already quite late on a Friday. And by the time the tests have actually passed, it was, I don't know, maybe 7 o'clock on a Friday. But we were very excited. So we really wanted to merge this in and have it nice and ready for us on Monday morning. We do have a culture of merging things in once all of the tests pass. So we were brave anyway, and we decided to just go ahead. And things were looking good. Over the weekend, there were no issues, no alerts, nobody got woken up. And we were quite happy and came in on Monday morning, and of course this wasn't the end of the story. We were horrified to find that incremental compilation was taking 10 to 14 seconds, and that meant that every single time you made any change, you had to wait for that long before you could do anything else. And this really sucks. So after doing a little bit of digging, we found that ECMAScript 2015 and TypeScript consider any module with a top-level import and export to be a module, and otherwise it is treated as a script on the global scope. And that meant that it gets completely recompiled and rebuilt from scratch every time. So the fix wasn't going to be easy. We either needed to move 100% to TypeScript, or at least 100% to use import and exports. So we needed a battle plan. Basically, we needed to go from something like this, with require and modules.export, to something that looks like this. However, we also had a bunch of code that was doing this, so this was really going to be a challenge. Next steps were to start rolling out TypeScript to our mini repos. We decided on a few simple rules to help us with this. Rule 1, convert all templates to TypeScript. Rule 2, all new repos are TypeScript and convert as you go. Rule 3, all new files are TypeScript and convert as you go. And last but not least, keep track of your progress. So let's dive in a little bit more into each rule and how we implemented this. So if you have any template repos, you want to convert them early on to give everybody the best chance to get started with TypeScript at the very next new repository that they have to create. So think of this as your absolutely ideal future repository. So this is your chance to upgrade some tooling. This is also your chance to use maybe a better test runner. So we've actually changed from Tap to Jest because it was a nicer tool to use and better TypeScript support. And now that you have a shiny new TypeScript template, that means that the next time you have a repo to create, you can go ahead and use that. However, if you're working in an existing repository, you want to try and convert those early on. So we agreed that while planning for our next feature, we would incorporate a little bit extra time into all of our estimations so that we had a chance to refactor the existing code base before adding anything new on top so that we could be working with TypeScript. And this may sound like a lot more work up front, but in reality, this has helped us to move faster, and it worked so well for us that this has actually become the standard on the team. So every time that you wanted to make a change, add a new feature or add a fix, you would refactor that area of code first by converting it to TypeScript and updating the module imports, and then you would go ahead and put your feature on top. And my team was really into incremental delivery, so we applied the same thinking to our TypeScript rollout as well. essentially breaking down the rollout for any repo or file into as many small steps as possible, so that the next time you're in the code base, you kind of could continue and adding small incremental improvements every single time. So the basic kind of steps were that we convert the repo to TypeScript, but allow JS, just like I've shown earlier for our very first conversion. Then you would convert all the files to .ts with the absolutely minimum amount of changes. So just updating the imports where you can and adding some basic types. You may also initially need to relax some TypeScript rules, but ours were so few and simple that it didn't often trigger anything. And you can do it all at once if it's a very small repo or file by file, depending on what you're working with and how much time you've got. And then continuously improve this with every single pull request. So you could go back and convert another file, or if you're making any kind of change at all, find something small that you could also update. So first we convert the absolute bare minimum and allow JS. And this is what that might look like, where it's just a couple of small changes to how you are compiling your project and maybe how you're testing it as well if you're doing some of those updates. Then we said that we would convert all the files with absolutely minimum changes. And this is where the same kind of updates to the import and export statements would need to be made, and maybe a couple of small adjustments in order for the compiler to not have errors. We also took this opportunity to use arrow functions everywhere that we can, and also try and get rid of as many promise chains as possible. So this was our time to kind of improve and refactor all of those things that we wanted to do at once. And then continuously improve this with every single pull request. So for all three, we said that all new files will be created as TypeScript, and you would convert any existing ones as you go along. And the exact same principles will apply with incremental improvements, where you would convert the file that you're working with to TypeScript and do as many changes as you can afford time-wise in order to improve the area of code that you've touched. But also add a couple of things to make sure that you are making the most advantage from having TypeScript in the repo. Add some basic types, especially for function parameters and the function return values. And that immediately unlocks so much goodness throughout your codebase. And last but not least, it was really important for us to keep track of progress. You want to know how you're doing. You want to see the progress is happening, especially when you have 300 repos and you have lots of different teams that are contributing. So having this goal and also being able to monitor how you're doing was really key for us. So we started out initially by writing a small script that was able to count the number of files that were TypeScript versus JavaScript. And at the same time, we also counted the number of promise chains that we had, because we also wanted to get rid of those as a goal. So then we were able to post little motivational weekly sort of messages where we could see the TypeScript percentage going up and up and up over time. And here's the script if you're interested in taking a look, and you can update it to do whatever it is that you're looking for, to count either the TypeScript lines of code, or maybe you wanted to count the number of promise chains that you wanted to remove as well. And maybe 3 or 4 months ago, we were actually able to completely remove allow.js from a main application and many other repos as well. So that meant that no new JavaScript files were allowed whatsoever, or in fact, any JavaScript files were allowed in the repo. This was absolutely great. What have we actually learned from migrating to TypeScript? What I've learned is that as soon as you convert even one file to TypeScript, you get immediate benefits. You suddenly notice all of the unused variables lying around, unused functions, function calls where the parameters are in a completely wrong order, function calls where the parameters that are required are actually missing, and test marks that are completely the wrong shape and therefore makes you really be dubious of what those tests are testing and why are they passing. So there was a lot of surprises and eye-openers, and it did make you wonder how some of the code worked at all. But the most dangerous mistakes that we saw were the ones where the code did something, or you thought that it did something that it in fact did not. So let's take a look at an example. Let's say for some reason we want to always calculate the bill tip after you have eaten out at the restaurant. And based on the call size of the code, Alice thinks that we need to pass in the total and then we need to pass in the country code. However, quite a long time ago, Bob refactored that function and it no longer requires a country code, it is just a constant. And maybe there are lots of steps in between the original function call and then the actual function being called. So it's hard to trace how the parameters get passed in through the entire chain. So Alice believes that this country code is for some reason important, and in fact gets surprising results whenever she changes the country code. The value returned doesn't change at all. And this can be quite confusing because you think that the code is doing something, but the code is doing something entirely different. And again, JavaScript is not going to complain just because you're passing it something a little bit extra. It's just going to get ignored. But the fundamental understanding of how your code works is completely shifted because of the parameters not being utilized. The next example I call, you wanted a cat, but you got a cat without a tail. What am I on about here? Let's say that our main application needs to be able to generate a new cat. And in order to do that, we have a cat service, which is a cat microservice, and they speak to each other via this cat API. So our cat type extends an animal and adds the extra tail, whiskers, and some meta, which is specific to the cat. And let's say the cat meta, we want to know whether the cat is vaccinated, its given name, and favorite snack. And the animal might have some basic things like ears, eyes, paws, and the animal coloring. And the animal coloring could be ginger, mixed, or black. So if you create an interface for a cat body type, the request needs to have the cat meta and then the cat settings, which is the color of the cat to generate. So let's create our fetch cat function. And this is where we can populate our body and say that the meta is to be the given name of Fluffy, and the cat settings, we want the cat to be brown. And then we're going to make a call to our create cat request, which is going to speak to our microservice, and that returns a cat. However, looks like we made a mistake. Brown is not one of the assignable colors, so we actually need to pick from ginger, mixed, or black. So let's fix that up. Okay, so our kitty is now ginger. So let's take a look on the other side. So this is now our cat service, and once it receives the request, is going to use the cat data that it has and it's going to generate a cat that's going to have eyes, ears, paws, which is from our animal base, and then whiskers, coloring, which comes from the request, and given name, which also comes from the request. So what happens if we share the types that we've created between both our main application and this microservice, so that we could make sure that we are, using the same types all around? So let's add that in. But as soon as we've done that, we're actually going to notice that we are not returning the property tail. And that means that this whole time that we thought we were receiving these cute, adorable cats we were actually getting little tailless monsters. With TypeScript, refactoring becomes so much easier. You can type the input and output of a function, and then you're free to completely rearrange everything in between, because TypeScript is going to help you make sure that you are still returning the correct shape of whatever it needs to be. You can mock the boundaries much better. Just like we saw, you could share the types across multiple microservices and multiple apps. And that's also really helpful when mocking out the tests, so that you have a realistic boundary that you're testing against, and that you notice that if you're sending back little tailless monsters instead of cats. Thinking about wider context is something that naturally happens when you have TypeScript in your repo. And this is because you can't type just one instance of something. Because of type inference, if you didn't type it quite correctly, it's not going to compile. And if the same object is being used somewhere else in a codebase far away from you, you will be forced to review both usages and understand how it's being used in all areas of your code before you can create a type that encompasses it correctly across everywhere. And that means that it completely broadens your understanding of your code base, which is absolutely great, because suddenly you understand how this function might be used in different contexts and how it needs to behave in those different contexts as well. And that also means that you would start noticing things that don't quite make sense, and that would push you to improve the architecture of your code as well. Thanks to TypeScript, our code has never been in a better shape, and I actually can't imagine not using TypeScript anymore. Thank you.